Hello, hello, hello. Hello, Joshua. All right. Hello, hello, Jalila. All right. Hello. Good morning,
Morning.
Jalila. Okay, and good morning. Good morning. Oh, voice and chat. That's awesome. Good morning, Nadine. Awesome. Good morning. More? Okay. And we're not gonna. Okay. Good morning, Luke. Okay. Oh, awesome. In the chat as well. Okay, I'm doing the chat quick. So, good morning, Josh. No, sorry. Good morning, Nadine. Good morning, Jalila. Good morning, Josh. Good morning, Mohammed. Good morning, Luke. All right. Oh, good morning, Alicia, with the video. Awesome, awesome. I hope you guys, I think you guys are getting the deal. All right. And I think you are because I think you all many of you turned in a bunch of things already and got them back. So I think you're getting the deal. Awesome. I still don't know. I'm experimenting with these different. I'm going to try a different immersive view every day until I prove that they don't put you in the seats, which is so weird. Although maybe it's better. And good morning, Jaden. I believe I'm saying it right. Okay, we're going to switch to view in a second, but we're going to get rolling. We're going to get rolling. We're going to get rolling. Uh, yes. Okay, that's what we want. Oh, more people. Okay. Um, we're going to continue with where we were Monday. Welcome back. The deal with today now, I'm going to start flipping the pages of the board in a second. I will change the view in a second. I know this is distracting, but it's a little bit fun. But I will change to a normal view in a second. What we're going to do here, as you see on the board, I'm going to start walking you through the solution to the first part, the very first question of homework 1A. So the homework that's due Monday. Okay, I'm going to do a quick screen share so you know what I'm talking about, and also so you can watch in the recording if applicable. Like we're about to start. We're about to start walking through this. This is the homework due Monday. It's homework yeah, Monday. It's homework 1A. And Monday, of course, we meet. Am I all confused? Yeah, we meet in person on Monday. So you'll turn this in before class begins. You'll turn in your first draft of your responses to this sheet um, before we meet in person on Monday. I'm about to start walking you through like the very first question, just to show you. I'm going to give you the answer to the first question. I'm going to show you what I'm looking for. You know, so for all of you, will hopefully help you get rolling on this particular homework. But for those of you who also, don't know me or didn't have me last semester, it'll also show you like how to present homework and exams to me in this class. I.e., I'm going to be showing you what I mean by of the five-step method uh, um, and self-sufficient document. Um, yeah, so that's what we're going to do now. Just picking up from where we were yesterday. Now, obviously, you can stop me at any moment with any questions. I'm going to switch the view on the screen so I can um, yeah, and remind me, and I think I told you the grading policy, but how the numbers work. If I didn't, let me know. But I think I told you. In other words, every single one of these homeworks and every game or participation homework, every single one, whatever the point value is, you just divide in your mind by 50. And that's the number of extra points that will go on your final exam average, your exam/lab average at the end of the semester. I'm just going to say this one more time because it's simpler than it sounds and it's simpler than it seemed last semester to many of you. So and I've sort of programmed Google Classroom to help you track this as you go now. It won't do it perfectly, but it'll help. Okay, so what I'm saying is again, just for anybody who missed this Monday, by the end of the semester, you have a midterm exam, you have a final exam, and you will have a final lab average. Those three are equally weighted, averaged together to get your base average. And then added to that base average is the total accumulation of all your points on all kinds of homeworks, this kind, participation, anything, all those point values. You take the full lump, you divide by 50, And whatever that total is, you add to your numerical average in the course. Okay, so when this homework says it's worth 50 points, up to 50 points, what that really, you divide by 50. What that really means is if you get all the credit eventually on this homework, you'll get an extra point, added to your exam slash lab average at the end of the semester. I'm saying it again because if I say it enough, I think it's actually simpler than it's unusual, but it's simpler than it may sound. And again, simpler than it may have seemed last semester for some of you. So, and last thing about that too, I think I'm experimenting now. I'm trying to make things better. So Google Classroom, I think if I do this right, I'm starting it, will give you your total points as you go. It will keep record. You can find out at any time from Google Classroom how many total points you have from all your homeworks and all your participations. Just remember at any moment, whatever that number is, divide it by 50 in your mind and that, or on a piece of paper. And that's the amount of points you'll add to your exam average once you start having an exam average. Okay. Can I just get show of hands? Is that sort of clear how you could track your grade as you go? Because I think it's stressful if you can't. I mean, I know it's stressful. If you can't. Wait, I can't even see the hands because I'm screening sharing. All right, wait, I'm going to switch the view. Wait. There's something in the chat. Wait, okay. Wait, I'm going to stop the share and I'm going to switch to view the screen. There's a lot of things. Yes, in the chat. Yes, and yes. Thank you guys. And remember, that's also points. You could submit those for, that's called closing a conversational loop. That's called answering a question. That's called various things. You just find it and you can get points for those. Okay, I think you get it. I'm going to switch to start going over this from the board yesterday. Oh, sorry. Ah, why up? Sorry. Here it comes. Okay, so that's where we were, and I know this is I don't know. Actually, tell me privately later in the chat, these crazy views that I'm trying just sort of be fun. Um, I assume they do not help, but tell me in the chat later if they help, if they just even keep you awake more or help the recordings more. Just tell me privately, whatever. I'll look later, but okay. But I am going to change because I think it's ridiculous. At the moment, it's ridiculous. Okay. So, okay, so getting to the homework. One more just logistical or policy thing I want to make clear if I didn't. The way I'm saying this homework, this is now everything I'm going to say from here on in today is about the real homework, the problem solving, many point worth physics problems, such as the one we're about to go over today, homework 1A. So everything. So in terms of policies, it's due 9/25 Monday. What does that mean? That means as long as you submit a thorough, reasonable, proper, respectable first draft by 9/25, a first draft according to the procedures like I'm about to show you, as long as you submit a first draft by 9/25, then that means no matter what score you get on it at first, you can keep submitting revisions according to you could keep submitting revisions until you get a perfect score on it. You can always get full credit on all the homeworks. But as long as you can keep up and you have the time and the energy to keep doing revisions, okay? That is if you submit the first draft on time. If you don't submit the first draft on time, you still can get credit for the homework. It's still better late than never. You just won't get all the credit and you can't go through like a whole big revision process to make it perfect, okay? I hope that's clear. Anytime you get a first draft back, even if you think it's a really low score or you're frustrated or this or that or whatever, as long as that score is more than half credit, that is a signal. Even if, for example, even if I turn it around really quickly just to say, thank you, I got it, but I don't even give, for whatever, sometimes I do this, like don't even put extensive feedback on the first draft. As long as you got more than half the credit, that's a signal that I'm acknowledging. I know you are on time and thank you. So you're good to launch revisions. It might be that I might be trusting that you'll learn how to do the revisions from things we say in class, because as you will see, We assign homework for you to try to work out on your own, and then we go over it in class. So you have to try, and it's like hard at first. Then we go. So it sometimes it may just be like, yeah, you're gonna. I know you're gonna make a revision based on stuff I'm gonna say in class. I'm not gonna even waste either of our times by rabbit holing with your draft in the right now. I think you get what I'm saying. I tend to look more closely at subsequent drafts because they're better. Okay, so I think that's what this says. Assuming you submit a thoroughly, properly for your first score will be more than half credit, and feedback will start coming on subsequent drafts. I mean, it might come before, but some. Oh, and so last thing about this too. Again, this is for people that don't know me. That also means if you submit a first draft and for whatever reason you get back a provisional score, and maybe not a lot of feedback on that first draft because for whatever reason, I'm trying to keep the machine going. And then you come to class and I go over the whole thing or I go over a lot of it and you're quite convinced, wait, hold on. Like I actually did think I did everything here and I think I did it right. I don't know what the problem is. And maybe the problem is I haven't even looked that closely yet, maybe, right? So if you're pretty convinced that your first draft, that you don't like your score on the first draft, you're pretty convinced I haven't really noticed that you really did a perfect job. All then you have to do is just re-upload that same draft a second time and just say re-uploading for your perusal. And basically it's the ball's then in my court. So eventually you either get feedback of what I need you to do or you get all the points. I hope that's clear. And there's one more thing. Sorry, there's one more thing about all of this with all the homeworks, with everything. As you can see, I'm trying to teach. I believe that everything is a draft and that things go through many revisions. I'm trying to show in this course that we do things over and over in science. We don't get locked in to our first attempt. So therefore, and again, stop me if I'm going too slow or too fast here. But therefore, I am saying to all of you, whenever you put a second thing up in a homework portal, either a second revision of real like physics homework or a second time that you showed video, in a game portal, participation portal, anytime you do another thing, leave the old one, all the old ones up. It's super important. Don't take down your old drafts. Leave them all up. It's so much better for you and for me to see how hard you're working and how many times you're trying things. So always leave old things up. The way you do that in Google Classroom is when you're about to attach a new thing, you first have to hit the button that says unsubmit, or I think that's what it's called, unsubmit. It doesn't erase your old draft. It doesn't erase your grade or anything. It's just basically saying, wait, I'm going to do another thing. It's just to notify me that you want to do something. So you hit unsubmit, you attach new document, then you hit submit again. So then that will notify me to look again at your old grade and then make your grade higher. Okay, I hope that's clear. I'm going to go, oh, okay, sorry. Huh. Oh, thank you. I see in the direct chat. Thank you for the feedback about the background. Very helpful. Thank you. And I'm not going to call you out because you're direct chat, but thank you. And you should screenshot you should submit that for points that you're giving me feedback on. So it might even go to more than one portal. You could even say there's a portal for respectfully corrected where you respectfully say the professor was wrong about something. I don't know if this is like a matter of right or wrong, but you're certainly respectfully giving me constructive feedback. So at least put it in that portal, if not something else. You know who you are. Thank you. Okay. So, but quickly, I know we all want me to get to the physics. I want to get to the physics. Are we sort of clear so far? Can I move on? Like, are we clear on the grading and the stuff? That's a yes, sort of, Nadine. Thank you. And thank you, Alicia. Okay, great. And thank you, Jalila. All right, so we're going on. Okay, so it just said this. This is what this says. I just said that. Like, again, always hit unsubmit first, then put a new draft up. Oh, yeah. Okay, it says that. You got it. All this will be. All right, so we're now. Whoa. Oh, no. A page got deleted. Oh, no, it just got out of order. Okay, hold on. Okay, so now we're gonna go. Here we go. Finally, 9:40. We've got an hour. Okay, that's good. We're going to the first homework now. I'm being you. Like I'm giving you right now. I'm trying to be the student, pretty much giving you an example of what I would want from you on any kind of physics homework like this, and on exams, assuming we maintain the same exam format that we have in the past, which I think we will. So first, notice I'm like on a blank piece of paper, right? I'm starting from scratch. I'm ideally doing this on actual paper or on a tablet. It's fine, but I really would encourage you to use your hand and a stylus or a pencil, unless, to be honest, unless you happen for other reasons in your life to know how to type in in LaTeX, which is like the technical writing format. That unless you know how to do that, or I would just encourage you to do these things by hand and then scan them in PDF. That's not a requirement, but that's an encouragement. So, okay. So I started doing the problem. I wrote homework 1A on the top thing on a spring. Okay. It'd be nice to have my name too, but you don't even need your name because it's Google Classroom. Okay. Then I start right away with a diagram. I am starting with step 1, DFP. Now, again, I think I mentioned this Monday. In Google Classroom, there's a number of different documents under tools that delineate what I mean by the 5-step method, but I'm showing you right now. The first step, it's a 5-step method you do for everything, for every sub-question of every problem. Step 1, DFP, means diagram and fact pattern. You're going to present a diagram and a fact pattern first thing first. Now, many cases, I've already given you a diagram in the problem. Fine, great, that's helpful of me. But you don't copy and paste that diagram. You make your own version. Could you use a computer for this? Sure, sure, sure. I mean, could you even use AI if you want to make your diagram based on the facts? Sure, that's fine. I mean, that's a good use of AI. But you don't just copy mine, and you do the diagram whether or not I gave you one. Sometimes I do, sometimes I don't. But we need to start with a diagram. The standard and you'll notice in my diagram, oh, sorry, is there something in, okay. In the diagram, well, first of all, you'll notice there's a coordinate system labeled. Like I chose to call everything this is a one-dimensional problem. So my coordinate system is simple. There's only one axis, but everything to one direction, I chose to call positive. I mean, I chose to make everything to the right positive, everything to the left negative. Your diagram might be different. You could flip it left and right if you're a left, if you want, for whatever reason, or you speak Hebrew, like honestly, whatever, that's fine. You could label the other thing negative from what I labeled, that's fine, but you make a choice and you label it. Then also notice, this is part of the purpose of the diagram, is to get the coordinate system clear from the get-go. Also notice in my diagram, there are labels. I mean, it's not a beautiful diagram, but there's things like M, K, X, X naught. In other words, and here's the key of the diagram. It's obvious, but it's not obvious. The key, really, the purpose of the diagram is twofold. Number one, we use math as our language, but our content is physics. What distinguishes physics from math is that physics is about what's happening in space and time and the lab right? So we need a diagram to show this is a visualizable situation. It's not just abstract relationships. That's number one. But number two, when we get to the math, which of course is like huge in physics, once we start doing computations to solve this problem, we're going to have a bunch of letters, X, M, K. We're going to have a bunch of variables and constants. They don't mean anything to a reader unless they got defined initially. How do they get defined? They are labels in the diagram. So the first real standard of what I'd be looking for in a diagram is it. And the purpose of it is do it your own way, do it in your handwriting, use your colors, show that you've personally assimilated the situation, and make sure that every single letter that is going to appear in your computations down below appears as a label in the diagram. Bottom line, the real purpose of the diagram is the labels. So I label M, I label K, I label X, V naught, whatever. Then this is what I mean by fact pattern. Then underneath, if it happens that the problem presents actual numerical values for these constants and variables, which often is not the case. Often there aren't even numerical values. But if there are numerical values, then I sort of list them and any other related facts, like below the picture. That's why I call this diagram and fact patterns, like the diagram, and then what are the particular like measurements or whatever applicable to this. So I have below by K in this case. It mean like what K means is like the stiffness of the spring, but what happens to be in this case is 200 newtons per meter, etc. Okay, so that is step one. I'm looking at the chat. There's nothing. Okay, we're good. That is step one every time. DFP diagram and fact pattern. And I'm dragging this out to show you all, even though obviously some of you have seen this before. But I want to emphasize not only is this what I want, and this is how you do exams and everything, but this is how I grade. This is what I'm looking for is these steps. This is, in fact, I'm trying this semester, you might have noticed, it's not just how I grade like tacitly or sort of ish. It's actually, it's an explicit grading rubric. So this is like where you gain or you gain points for doing this stuff, even if you don't know what the final answer is or can't get there or think you can't get there. This is the path to get to a final answer, and you're getting credit as you go by walking down this path. Okay, so all right, so that's step one, DFP. Now we're going to get to, whoa, oh God, what is going on with the pages here? Sorry, hold on. Step two, okay. Okay, then we get to step two. I want to say, but also notice now, please, because if you look, before you do this homework, if you look, there is actually a grading rubric in the assignment portal. That is not something I did last semester with those of you who know me. So, but it is now. I think it's going to make it better for everybody. But you'll notice it. So you'll notice that part of the grading rubric is also self-sufficient document. What I'm giving you here is an example of what I mean by a self-sufficient document. First and foremost, I am not writing on the original sheet. I'm treating this like a blank blue book, right? I'm giving you a document that stands on its own. I'm not copying anything from the original sheet, but also I'm not assuming anything from the original sheet. Do you notice I'm not screen sharing with you guys right now? I'm walking through this and I'm not going back and forth between the two screens because in principle, the way I'm presenting this, I'm giving you all the information, you, the reader, all the information you need to follow what is really a mini derivation of a physics situation. This is meant to be a physics situation that stands on its own. Sure, a teacher asked you a question, but your job as a student is you're turning your answer into a piece of independent physics work. I don't need to go back and look at the question to evaluate or to understand your answer. That's what I mean by self-sufficient document. Not only is none of the original thing included, but also none of the original thing needs to be referred to. No other context needs to be referred to follow this. You could give it to a tutor and they could tell you if it was right or wrong without looking at anything else, is the idea. Or you could submit it to a journal and they could tell you whether they agree with the physics or not without looking at anything else. That's what I mean by also, you'll see in the grading rubric, what I also mean by self-sufficient document is that everything you're saying here, or I'm saying here, even if I learned it from any number of sources, including AI, what I'm writing here is what I'm writing here, having learned it. I'm putting it through my words, right? Like, in other words, this is not a robot. You follow what I'm saying. I'm going to keep, but that's part of the metric, or the grading. That's okay. So now we're on step two. I'm looking at the time. I'm also, oh, I see in the chat. Thank you. No problem. Got you. I appreciate the acknowledgement. Direct chat person. All right. So now I'm up to step two. Step two is WIQ. What is the question? So important, so important, and so easy to overlook if you don't think it's important, like because it seems so obvious, but it's totally not. And I should have said this a minute. It's part of what I mean by self-sufficient document. You are now, in your words, and hopefully words that are simpler and shorter, or maybe even more symbolic than my words, you're just going to make clear right now what the undertaking here is. The undertaking of question one on the sheet is at x equals x naught. What is F? I mean, the sheet put it in English and it was written by me. So it was like too much English, probably. You're distilling it down to its essence. You're not leaving out anything that's important, but You are, in the simplest, most straightforward way that shows that you understand, you are capturing what is the question. The question, and that includes whatever condition the question is specifying. So the question is, at when when the mass is at its initial position, what force is being exerted on it by the spring? So there's a question, and you could say it symbolically, but it's a complete thought. At x equals x naught, what is F? That is what we're right. If this were a research paper, that's your research question. Okay. So that is step two. What is the question? Again, if that's not there, this document doesn't stand on its own. Also, it really, I don't want to go off on a rabbit hole, but I cannot tell you how much it'll help you as questions get harder and harder, and you more and more possibly have that feeling that we all have looking at physics, which is, I don't even know what this thing is. I have no idea how to begin. Like, what is he even asking me? Actually forcing yourself to try to figure out what I'm asking you is an enormously important, helpful way to progress. So what is the question? I'm going to move on. I promise I'm going to move on, but there's one other thing I was going to say about this. Step two, what is the question? Oh, yes. People sometimes ask, and I need to put the following, I need to put this more explicitly in the grading rubric, but if you're wondering, are we supposed to actually be labeling the steps as we go the way Yaverbam is? Yeah, that would help. I mean, it couldn't hurt. It will only help if you make it clear as you're going. Here's and you don't have to use my words again. You could just put in a different color somewhere. You could be like the question, the diagram, the next thing. Like, yeah, label it. Why would you not? You want to make this as easy and inviting on the reader as possible. Of course, I suggest that you look at the grading rubric before you even do this if you want, and you'll see what I'm looking for. Okay, but that's step two. I'm looking at the chat. You could stop me at any time. But now here, and that is literally the question for this. Like, obviously, these. Are you just going to copy this for your homework when you go home to do this for Monday? Well, yeah. I mean, I am doing it out for you the first one, then you'll do the rest. But even here, it's an exercise. Like, don't literally take a screenshot of this and send it to me. I recognize my own handwriting. I mean, since hopefully this is straightforward enough, this question, just do what I'm doing, but in your way, with your words, with your colors, personalize it. Um, yeah, okay. So question three. Okay, I mean, sorry. Step three, GDP. GDP stands for, well, sorry, my handwriting's bad here. It stands for General Definitions and Principles. General Definitions and Principles. What do I mean by this now? Well, first of all, I tend to mean things that can be expressed with triple equal signs rather than double equal signs, for those of you who are familiar with that distinction. But more to the point, I mean laws. I definitely mean definitions. Definitions, laws, relations, equations, if you like, statements of physical truth that we know about the universe even before we started looking at this problem. Step three is what we know about the world, about physics, before we started even looking at this problem. I want to pause on this because this is one of the more subtle steps now. This is a step where it really kind of separates the women from the girl, the men from the boy, the people from the person. Like, this is subtle. And it's basically, this is a step where it starts to get into like whether people are really like getting an A in the course or a B plus or something. Not to be, because okay, so let me back up. So bear with me for a second. This is a very important step. And it's like it ends up making a big difference in your point values, like how you're doing these homeworks and exams. This is step three. So first of all, what most people know from like seventh grade, when you're problem solving, most of you are familiar in one way or another with some kind of thing of like first write down what you know and then use it to figure out what you don't know. I mean, like, right, I agree with that. We are, in effect, I'm saying first write down what you know, what are givens, and then start doing computations. But I'm here to tell you from over 30 years of experience, what made life hard, what was a breakthrough for me at some point in my experience was realizing, wait, there's different kinds of things that I know when I start a problem. There's some things that I know from the actual problem. That's step one. the facts of the actual problem is step one. And then step two is like, all right, so what is the problem of the problem, right? What is the question of the situation? But then step three is, okay, so what did I know walking into this problem that will enable me to solve it? Now, that that means laws and definitions, things I'm confident of before I walk in. Often things that might require a little reminder or a little context or a little brief explanation, but don't require a ton of proof or anything because they've already been established in this physics class or the physics class right before it, or maybe in a calculus class. In other words, this is where we write down things that we've already come to establish as truth, as definitions or as laws or something. And therefore, some little explanation of what they mean might be helpful, but a big proof or derivation wouldn't be necessary. So we're going to use those laws to solve the problem. So on the one hand, I'm saying this is where you have to start thinking. Like, am I going to use? For example, here I'm going to use Hooke's law. You see already on the page Hooke's law, because Hooke's law tells you the force exerted by a spring, and we're looking at a problem about a spring. But Hooke's law was true whether or not we were looking at this problem, right? And the next question, we might use Newton's second law, F net equals ma. In fact, we definitely do in the next question. The question after that, hint for anybody, pro tip for anybody who's still paying attention. By the time you get to question 4 and 5, the principle you're going to want to write down is the principle of energy conservation, like principles about kinetic and potential. And I'm warning you right now, pro tip, by the time you get to question 4 or 5, you're going to want to be very clear in your mind and deliberate about exactly, you're going to want to use energy by the time you get to question 4 and 5, or something about work and energy, or something about kinetic and potential energy, depending on what instructor you've had in the past and how you think about energy. There's different ways to think about it, many of which would work. But you're going to want to be specific. You're not just going to want to write down like a formula like K equals 1/2 mv squared. Like that's a start, but that won't be enough. Number one. Number two, so this is where we start setting up the table in order to do the work and eat. And it's much easier to do this step 3 if you've already properly done step 1 and step 2. But what I'm also warning you, and then I'll move on, this is also the place, especially in exams and stuff, where I look closely, because here at this step, if we just suddenly start writing down formulas, and I don't like that word, I don't use that word, you'll notice, except critically. If we in this step start writing down formulas that we got from the web, or that we got from AI or whatever, even if those formulas are correct, if they're out of nowhere, if they violate self-sufficient document, if they're just some formula that some robot said is true, well, it might be true, but if we've never established it before, if it's the result of some long derivation or even short derivation that we've never established in the logic of this class and isn't being argued here in the document, then that is not right. Okay, step 3, you got to write down something that's true and helpful to the problem, but that is coming from somewhere that we could all agree in this context. And a quick reminder of why, like, because it's been established, it's a definition, it's a law. It can't just be a random formula that happens to work, but okay, I think you get my point. I'll move on. But so I scrutinized step 3 somewhat intensely. So in this case, it would be F equals negative kx. That is a law of physics. That's a straightforward law. And you might even write here, and I believe we established it at the end of physics 203, at least in most courses. You might even write here, provide a little graph of what it means. Like you might, just to like, oh, sorry, that's not what it means. Sorry. And I'm also looking at the time. Oh, we're good. This goes to, oh, we're good. Um, Um, like now this is just my little version. You would give a different version. What does it mean F equals negative kx? It is Hooke's law for a well-behaved spring. It's the force that the edge of the spring exerts on anything touching it, assuming that the other side of the spring is like held rigidly. And it says that it assumes that a spring has an equilibrium orientation, that if you fix one side of it, then the other side of it will, that there's one place where the other side likes to stay at rest. If you place the free edge of a spring at a certain position, it won't move from that position. That's called equilibrium, and we usually designate that x equals 0. The law says that if you displace the edge, if you put a mass on the edge of the spring and you bring that mass, you try to hold it to any other position besides x equals 0, the spring will exert a restoring force on that mass to bring the mass toward equilibrium, right? This is what the law says. It says that if the mass is like 1 meter to the right of the equilibrium position, the spring will pull on the mass to the left. So if you let the mass go, it will start accelerating to the left. If you hold it to the left of the equilibrium, the spring will pull it to the right. Hence that negative sign. The spring will always exert a force that is in the opposite direction, that is directed oppositely to where the mass is relative to equilibrium. Right? That's what the negative sign means. But furthermore, the fact that F equals negative kx, as opposed to F equals negative kx to the squared or x cubed or something, the fact that it's F equals negative kx means that it's a linear relationship, which is very convenient, that it's essentially directly proportional. What it's saying is if you try to hold the mass at twice the length that you used to be holding it relative to equilibrium, then the spring will exert a force that's twice as strong. That the spring pulls harder and harder on the mass the farther and farther out the mass is from equilibrium. That's interesting. Like in a directly proportional way. Like unlike gravity, gravity is always trying to restore objects to the ground. If I hold something above the ground, gravity pulls down toward the ground. So in that sense, gravity is like a spring. It's like a restoring force towards some equilibrium orientation. However, the difference is with gravity, if I hold something at 5 meters or I hold something at 10 meters from the ground, either way, the force is negative mg. It's the same, it's a constant force. So the spring, the elastic force, is the first force we look at that is not a constant force. It is dependent on displacement from equilibrium, and it happens to be approximately directly proportional to displacement from equilibrium. So the graph of this is a kind of unclear graph. The graph of force as a function of displacement is a straight line graph. Happens to be in the fourth quadrant, not the first, because of that negative sign. I think you understand, if the displacement is positive and the force is negative and vice versa. But it's a straight line. Straight line means constant slope. Constant slope means constant amount of rise per run. The rise in this case would be the change in force. The run would be the change in displacement. So the ratio of force to displacement for any place on this particular spring, that ratio is a constant. We call that ratio K. K differs from spring to spring, but it's the same throughout all positions for a given spring. You'll see this in the lab, or maybe you already saw this in the lab. I think you already saw this in the lab. You had lab. Oh, well, you didn't because you will see this in the lab next Monday. I may be getting all the classes confused, but I believe you have lab on Monday, but you had it virtual. Oh,
Yes.
oh, yes. Oh, thank you. And whoever was that Delilah? No, who was? Well, whoever that was, you did. Oh, that was Lunar. Or no, oh, wait, Lunar has a question. Okay, all right. I'm going to stop for a second. Wait,
No, it was me. It was me.
oh, it was you. Oh, sorry, Lunar. Oh, great. Sorry. Thank you, Lunar. And thank you for that. Totally submit for like 85 different portal points, like right now, please. And she knows, they know what I'm talking about. And if anybody, with the portals, and if you're still new to this and you don't, let me know because you want to know, or have Lunar explain it to you. But wait, and there's all those things in the chat. So I'm going to take a breath for a second, but let me just wrap up this point. You'll see this in the lab that a given spring has a given K K is this ratio of force to displacement. So what does that really mean? So it's the slope of the line. Why would the line of one spring be steeper than the line of another spring? Because one spring would exert more force per meter than another, i.e., one spring would be more strong or stiff than another. So K is really a measurement of the stiffness of a spring, how hard it pulls on you per unit meter away from displacement. Okay, that was like a long, that was kind of a review since we sort of did it quickly at the end of 203. Some of us, that was like a quick little review, but I'm also saying it all to say you could put a little bit about that. Once you put the GDP is the pivot point of the whole problem, of the whole solution every time. The step three, it's honestly, I don't have any favorites. I have two sons. I love them both equally. I have a 5 steps in my 5-step method. I love them all equally, but really, honestly, step three is my favorite. Like that is the focus. If you can really know what GDP to pick and you can explain it a little bit, you shouldn't have to derive it because it should be old news. But if you can put it in context and show you get the principle, then you'll be off and running the step 4 and 5. So do something like maybe this little graph like I just did or whatever to show what we mean by F equals negative KX. Clearly I have to go on, but oh my God. Okay, wait. So there's things in the chat. Now, one of them, okay, wait. Can you also see it as what tools, knowledge, and relationships can be used to work on the house? Huh. Yeah, total. Oh, you can also see step 3 as what tools, knowledge, and relationships can be used to work on the house. Yes, well said, person in the direct chat. Now, also, person in the direct chat, about 35 minutes, 2 more steps, and a lot more question problems. No pressure. I totally appreciate it. And I do. And that does. So, someone is sort of reminding me of like the time and my pacing, which I am conscious of and self-conscious of this semester. And yes, I definitely have to get to 2 more steps, but so I appreciate that. And that person should submit for points. But wait, let me be clear too. My only goal of this class, honestly, I'm not doing the whole problem for y'all. My goal and what I did in the other class, I'm just trying to get through the first one with you guys, just to be clear. If I can get past that, sure, that'd be great. But no, I'm just trying to set up, I'm trying to fully finish all the steps for the very first question, just so that you all know. And then we're good. So no, I'm not trying to get through a lot more questions, but thank you, sir or ma'am. Okay. But yes, step 4. Step 4. Now, step 4 is particular. Okay, I'm going to say one more defensive thing. Note, if you think I just spent, if anybody thinks I spent a disproportional amount of time on step 3, take that as a note to self. You, please, when in doubt, spend a disproportional amount of time thinking and writing about step 3. Just saying. All right, step 4. Step 4 is particular application and work. This is where you now get into the work, the computation. This will probably be your longest step, especially when physics problems get, more involved. You'll probably have the most written down for this step, but that's because a lot of it is mechanical. I mean, it won't be that much for this problem. This problem is somewhat straightforward, but a lot of it is mechanical. A lot of it is the machine just going, right? The mathematical machine. And it'll just come out of you and on the paper if you really spent your time properly on steps 1, 2, and 3. So there might be the most written down for step 4, but I still think the most hard thought goes into step 3. So step 4 is where you do the work, what we've always sort of considered the work, where you'll plug in values, you'll track your units, you'll pay attention to scientific notation if applicable. You will also, now here, please write this down. It's not written on the sheet, but you'll see it in the rubric. And I'm telling you, step 4 is where you're going to want to interweave steps of computation with English annotations. Really, like this centers on mathematical computation, but if the computation is long enough or thick enough, then it's meaningless on its own. It's meaningless to the writer and it's meaningless to the reader. And if you look in the most advanced physics journals you want to, even there, where everybody knows physics and cares about physics, even there, nobody ever does that. What they do is they'll have a bunch of equate steps offset and centered in the middle of the thing. They'll have some steps, but then they'll break always. and have English either between the steps centered in the middle or around the steps, whichever is easier for you with your handwriting stuff. But this is an explanation. This is a presentation. This is a proof. And it's a proof not only of why the physics is true, but that you actually understand the physics. So this is step 4 is where we do the whole computations. We do the work. We do the work that you would think of as the work. But this is where we're also showing that even if we learned this stuff, and believe me, I did a lot, you can sort of tell. I did a lot of experimenting with this and playing around during January with ChatGPT and all that kind of stuff. I'm like, I'm all for it. It's great. It's cooler than I thought. But of course, I'm also, I have mixed feelings like everybody else. So here's what I'm telling. Like, if you take my problems and like put them into ChatGPT to learn how to do the solutions, Quark bless you, fine. If they show you stuff that you didn't think of on your own, and then you get insights like, oh, I should use this, Quark bless America. But I have played around with it enough to see, like, it's not going to spit it out in a way that communicates that communicates in any real way. You want to now take the knowledge and turn it into a personally expressive, like, little presentation or essay or article. So that's what happens in step 4. I didn't even really do it much here. There's not that much to do, but so notice I even start with the word here. What am I saying? I often will start my step 4 with here, meaning I'm now moving from general to particular. I'm zooming in or I'm zooming down from a law to a specific example. And what that really also means is any answers I'm going to get now with numbers, sure, they might be the particular numbers that were given in this particular problem. But if you really follow my reasoning, you, the reader, follow this reasoning, then you could then take this and apply it to any other numbers. It would still work because I'm really making that distinction. Here's how the problem works. So, okay, so here, K happens to equal 200 newtons per meter. X naught happens to equal 0.15. And the law is F equals negative KX. Okay, so I plugged in 200 newtons per meter times 0.5 meters. Obviously, this is not a very, complicated problem. And then I cross out the meters. So, that's an example of, and then there should even be more English there, honestly, but there's not that much to say about this one. So I plugged in, I did the computation. It's all complete sentences or complete statements. So now I go to step 5. Oh, I see something in the chat. That's awesome. Actually, I'll pause. Let me look in the chat. Wait. Oh, great question. Wait a minute. Wait. Okay. So now I hope for the person who is watching my pacing, and I do appreciate it, and I'm giving that person a hard time, but for the person that's watching my pacing, I hope it's clear that if I stop to now deal with questions, I hope that doesn't count against my time because that's what we're here for. So I'm getting some good questions in the chat. One direct chat question. I'm confused. What is the significance of the negative sign in F equals negative KX? Okay, I did try to say it before, so I'm going to say it again. I'm going to say it a different way now, but if neither of them work, maybe play the video again later. The significance of the negative sign is that the force exerted by a spring always pulls in a direction that is opposite to where the mass is relative to equilibrium. That's true, but that was not articulate. Let me say this a different way. The negative sign means that the force is always restoring. It's always pulling toward equilibrium. So if X, so this is why at the beginning, we labeled our coordinate system and we said, okay, call positive values. Let's say the positive values are the values on the right. Let's say that where this mass originally was, it told us the mass is originally at this place called X naught, which happens to be 0.15 meters. Let's say really it's positive 0.15 meters. Let's say that where the mass originally is, we're calling the positive realm. I.e., oh, this may be what's confusing you, person, and maybe other people. I'm assuming that this spring, this well-behaved spring, could be pulled, could be extended, but also could be compressed. Like there's an equilibrium position, and you'll see that in lab on Monday. There's an equilibrium position for this, where the edge of the spring sort of wants to hang out, where if you put it there, it wouldn't go anywhere else. But you could pull the spring out from there, or you could push the spring in from there. You could pull the edge to the right, or you could push it to the left in general. So let's say we're calling the right positive. Let's say that we're calling extensions positive, which is our choice that we make in step one. So the initial value of this mass is positive 0.15 meters. Well, what the negative sign means is that if you have to hold the mass at positive 0.15 meters, the spring, the direction of the force exerted by the spring is to the left. Like the mass is negative. Like the mass is in the right of equilibrium, but the spring will pull toward equilibrium, which means to the left. So the displacement right now, the position of the mass is positive, but the force must be negative if it's trying to get it back to equilibrium. Conversely, if it happened that the x value of the mass was negative 0.15, like if the mass happened to be sitting on the left side of equilibrium, then the spring would be pulling it to the right toward equilibrium. The spring would be pulling negative of a negative. It would be pulling the opposite of negative 0.15, i.e., you would be pulling to the right. So the negative sign means that the force is always opposite to wherever the mass is at any given point. It's literally known as a restoring force. I'm going to pause for 1 second because that was a very fair question. Very fair question. And I want to make sure. Hold on, I'm looking at the chat. Okay, thank you. So the person in the chat who asked that really good question that I think benefited other people, the person in the chat where I just like talked about it for maybe too long, who knows, we'll find. But that person just wrote, okay, thank you, I understand now. That is called closing a conversational path. There's a portal for that. That person should submit a screenshot of that, like, or just remind in that portal and say, I asked you a question, you answered it, and I said, thanks for the answer. That person could also submit into the portal, please go forward, because it's basically meaning we can go on now. You can see how important that is with me, because I won't otherwise, right? So I will now, but I want you to know, like, that's how this works. You drive, the more you guys can drive this vehicle of the class, like the better off we all are. So he or she gets, and that also answers somebody else's question. Okay, and I'm just looking at the chat and then I'm going for hooks. Oh, no, right. Okay, so Nadine's question in the chat, which is a great question, but it sounds like I'm gathering that Nadine's question was answered as well. So great. So I'm going to take that as a you can move on, yo, and I will. But great. So keep it coming, please. You get it. You guys get it. Also, I really appreciate it. I'm seeing there's a mix of students in the chat and in the private chat. Some students in there are people I've had before, and some people are people I've not. I really appreciate that. Shows that this is sort of working for both of us. So great. I mean, within a few weeks, I don't want there to be any distinction between people who've had this before and people who have. Okay, anyway, so that's step 4, or that was step 4. Now step 5. Step 5 is final answer circled. So you put the final answer. Okay. First of all, yes, you do need to circle it or boldface it or highlight or something, partly for my benefit to make this all easier, just so I can see that you see what the answer is. But it's also, again, if you imagine this is a journal article or something, the reader has other things to do with their life. I mean, and also the reader's not in your head. So it's you want to get in that habit of like, here's what we're trying to do at the beginning, we're doing it. Here's what we did. Here's the research question. Here is the finding. Like, and if it were a poster for a conference, you would want the finding to be freaking highlighted in the center of the poster, right? For everybody's sake. It also shows confidence. It shows that you even know because anyway, it shows a lot of things. So you want to circle your final answer. I see there's something in the chat. I'm going to get there in a second. But furthermore, now a little more detail. You want the final answer to be a complete thought. The final answer is not 30 newtons or negative 30 newtons. The final answer is that the force is equal to negative 30 newtons under the condition originally stated of X being equal to X naught. Like the final answer should absolutely bring us back to the original question of step 2, right? It should close that loop. And it really should be a complete finding, even if it's kind of maybe this isn't the most interesting finding of the world, but it's a scientific finding. Under this condition, the force measurement will be that, i.e. there's an equal sign in my answer. It's not just a number. Sorry, I'm yelling, but like you get the point. You just treat all of this. This is what you. I think you see the point. We're trying to turn my stupid physics exercises into actual physics discussions. Um, so that's how you do the final answer. Yeah, complete statement with unit. Oh, the units have to be there. The negative sign matters. All these things matter in physics. The negative sign is part of the answer. And refers back to the original question. So yeah, final answer circled. One last thing, since people are asking all these good questions about the negative sign, so the negative sign is part of the answer. If I had chosen a different coordinate system, if I had chosen to call right like negative, then that's fine. I could do that as long as I'm clear in step one. I'm calling this side negative for whatever reason, maybe because I'm a lefty, whatever. Um, that's fine. And then does that mean that my final force answer would be positive? Yes, it does. And as long as it's all self-consistent, that's fine. One thing I want to caution you is in this problem, it did happen to say that the mass is initially displaced or is at a position of 0.15 meters or something like that. You can do everything I just said, but then you would need to be clear that the initial position of the mass is a negative number. If you're willing to do that, great. But part of the reason I didn't do that is because that's a little bit less convenient and a little bit unnecessarily confusing. But you could totally do that. Okay, so I'm looking in the chat. Oh, there's nothing more in the chat. Okay, so the funny thing is, oh my God, the funny thing is, we've actually achieved the objective. We're not done. I mean, and just so you know, you are exactly as far already as the other section. Yeah. And yet we do have 20 minutes. So somehow we're doing it. So I will do the next one if you want. I'm gonna do it with a little bit more of your participation, but I will pause. So we're like totally on track here. Let me just see. So this is what's due on Monday. Um, this is what's due on Monday. Again, if you get it in early or whatever, this is what's due on Monday. Is there any question at all about either this physics or this procedure or anything in the class? We have a moment to like we are on track. So is there any question at all? I'm going to pause for a second. Okay. Then I'm going to keep going. But maybe I'm going to turn it a little bit more to you. I mean, I guess I'll also say this. Um, the questions get harder and harder in this sheet. That's generally the way of physics. They get harder and harder. In principle, it's review. In principle, um, until you get to question 9. Oh, and wait, and some of the questions are a little bit more conceptual. So the conceptual questions I understand, like question, okay, I'm gonna back up. Like the first 2 questions are sort of about force and acceleration. Questions 4 and 5 are definitely about energy. You definitely want to use, and again, you can use any source you want to remind yourself or look up things about energy. Have at it. Um, but just again, rule of thumb for self-sufficient document, just don't write down anything until you understand it. You're writing to express understanding. Okay, so questions 4 and 5 are about energy, or my recommendation is that you use energy, work, and energy to figure out 4 and 5. Then 6 and 7, questions 6 and 7 are kind of conceptual. Um, so they're a little bit less lending themselves to the 5-step method. So let me take a pause to say, for the rest of the questions, well, you'll see in a second, for the rest of the questions, you do still have to do the method. But what doing the method means is acknowledging each step as you go. So when I go to the next question now, I'm not going to rewrite the whole diagram, and you don't have to either. But what I am going to say is step 1 for diagram C above. Like I'm going to acknowledge the need for a diagram. I'm going to say, if you want to see a diagram, it's right there. You can do that, and that can work in a journal article, right? They don't you get my point. So you can do that. Or furthermore, anywhere, like if you get to one of the sort of conceptual, one of the questions, I'll tell you right, it asks like, I think it's question 6. I think it's question 6. How many times does the thing go back? No, it's question 7. How many times does the thing go back and forth um, before it stops or something like that? Okay, it's not a trick question. if you're thinking the answer is, well, it's under these conditions, it should go an infinite number of times until it stops. I know I'm a little bit out of order here. I apologize to the, but in question, whatever that question is, I think it is question 7, when it asks how many times does it go back and forth before it eventually comes to rest. If you're thinking, if your gut instinct is, well, wait, I mean, I think it should sort of go on forever if this is like an ideal spring, you're right. And that is the answer. And I'm telling you, yes, according to this premise of this problem, it should go on forever. A spring in a lab will not go on forever, but this spring evidently will. Why? Because because as you'll see in question 4 and 5, unlike in the lab, like we're not acknowledging any level of friction or something like that in this question. We are assuming, well, we're assuming no friction. So in question 4 and 5, we're going to assume that energy is perfectly conserved, which it won't be perfectly in a lab. Um, so when you get to question 7, and if you think the answer is it should go on forever, I agree with you, but that still requires some explanation. And I'm a pro tip if you're still hanging in there listening to me right now, the real answer is because energy conservation would mean that. And you could actually show that with the math of energy conservation. Like you can use the same method you were using in question 4 and 5 to actually show that it should go on forever. I don't want you to go crazy, but there's a long way of saying you can still do the step method, even when the question seems conceptual. If but if you get to step 4 and you don't think there's a lot of computation, or if you think something's not applicable, really, you can say step 3, not applicable, but acknowledge the steps as you go. That's really what I'm trying to say. Okay. As best you can. So I'll do, I'm sorry. Question 9 will be hard. Question 9 is that's when we get into the new material. It is hard. We're going to go over it big time on Monday, or next week, I promise. But I'm telling you right now, this is one of the reasons you get to submit a rough draft like early and then do revisions. I'm telling you right now, you're doing steps 1 through 3 in general to get yourself rolling with step 4. And similarly, in this homework, you're doing questions 1 through 8 to set yourself up to be in a position to have a clue in question 9. If I just ask question 9 out of nowhere without those other, it would be completely unfair and really hard to do, really hard. You have a shot at question 9 launches us into the real material of this class. You have a shot at getting far in it if you've really thought through questions 1 through 8. And again, in question 9, you can use online resources to help you if you want. But I am warning you strongly with question 9, I will not be disappointed if you write, I have no clue. That's not cool because you can do the first 3 steps without having a clue. That's the point of the method. You literally could do the first 3. You get 60% of the credit of the problem without thinking you have a clue because that's the point of the steps. They get you to a clue. So if you just write, I have no clue, that's not good. Similarly, if you get to question 9 and you just start writing down formulas that are on the web that we've never seen before, don't do that. Question 9 is also kind of a litmus test and a guide toward let's be authentic and honest here. Like I know how hard question 9 is. So if you start it and you get to question 3 or step 4 and then you get stuck, okay, especially in your first draft, you say, I am now stuck. I don't know what to do. I'll appreciate that and it'll be fine. You'll eventually get all the points. If you just start writing stuff that looks right, but you don't understand, that's not what we want. Okay, I think I've said enough. Okay. So we've still 11 minutes, so I'll do the next question. But hope I'll do the next question, or with you, I will. So now we do question 2. Um, okay, you see my point? All right, so that's step 1. So now step 2. And I'm writing well, it doesn't matter. All right, so steps. Um, Okay, also pro tip, sorry. I'm writing these abbreviations to get you used to them and so that you know what I mean if I write one of these abbreviations when I'm grading your work or something. But honestly, if you're really doing a self-sufficient document, people outside the class don't know what these abbreviations mean. So honestly, pro tip again, if you're doing this as best as you possibly can and going for the most points possible, even when you label your steps, either put a legend somewhere in the thing saying like WIQ from now on means what is the question or something, or use other English to, but just remember your audience is an educated person who's not in the class. So do whatever. So I'm really kind of violating my own thing by just writing these abbreviations, but I'm trying to save time in class here. Um, so step two, what is the question? I have to look back at it. I believe the question is what's the accelerate? Yeah. So the question is at x equals x naught, what is a? Right? Okay. I'm looking in the chat. Stop me at any time in the chat if you want. Also, I'm going to switch to view. Hold on. Sorry, sorry. No, sorry. Oh, you can't see what I'm doing, can you? Okay, well, anyway. All right. So that's step two. Step three. Okay. Oh, here's an example. I've already seen this on some homework that came in from the other class. You'd think this would be obvious. Okay, so step three, what's the GDP for step three? Well, we still do have F equals negative KX, perhaps. Like maybe we still need that. But specifically, we're now converting, we're now moving from forces to accelerations. So certainly this is now Newton's second law. Now that's a law. Like that, you almost, besides definitions, you almost couldn't get any more ground level than a law like Newton's second law. So that is a legit GDP. And another rule of thumb of what constitutes a GDP, if it's on one of the equation sheets that I posted under tools in Google Classroom, if it's on one of those sheets, that's a pretty good litmus test that it's fair game. It should be one that you've seen already that we've derived already. But if it's not on those sheets, but so F net equals MA is certainly on one of those sheets. But the law is literally, okay, this is the law. F net equals MA. Two quick points about this. Number one, it's F net equals M, or sum of the forces equals MA. It's not F equals MA, right? That just in life, that's really important. It's you add up all the forces on an object, and that produces the acceleration of the object. It's not any one individual random force that equals MA. Okay, so you have to either use the word net or put the sum symbol in there. Also, F net equals MA is a vector equation. That doesn't make such a big deal in this case. But it does mean that direction matters, negative signs matter, and it also really means that if there's more than one dimension occurring, F net equals MA is true independently yet simultaneously on all of the axes. Important to know. So that's the law. Like I'm writing the law like as it is. Um, I could even say something like, actually, no, I'll leave that. I'll leave that for the next step. Okay, but that's the law. What am I really trying to say? Based on homeworks that I've already gotten, from other people, the GDP here is not A equals F over M. I don't mean to be picky or technical, but I'm just trying to warn you and caution you, so you can get as many points possible. The law is net force equals mass times acceleration. Then you can algebraically manipulate that, and you should, to get that A equals F over M, like to solve for what we're solving for here. But that's doing work. That's step four. The law is F net equals MA. You see what I'm saying? Okay, so don't just write A equals F over M. Like that is definitely not a law. Okay, so we write that. Okay, so now I can get to step four. Maybe I give a little explanation of F net equals MA, but even saying that it's Newton's second law of motion is pretty good. So now step four, PAW. So I would say here, now watch. This is like English. Looking at the time, we've got 6 minutes. Okay, here, the problem is fully, D. Right. So the first thing I'm doing is I'm saying the vector nature of this law is, or I can even go like this if you want. Like I'm saying there's only one dimension to worry about. So that's it. I don't have to worry about three different equations and three unknowns or something like that. You get my point. So, but then second of all, sorry. Okay, now the only force acting on the mass in this case is the spring force, the Hooke's law force, the elastic force. So hence, it is true in this case that the sum of all of the forces is just this one spring force, right? So I can say, you see my point? Well, I'll just leave it at that. Like I had to get there. If there was more than one force acting, then adding them together would be equal to ma. But you get my point. So I do that. Overdo it is what I'm saying. Especially, and again, I know I'm going to go on my soapbox. I know that many of you could do problem one and problem two in your head, and problem three. Probably not problem four, but many of you can solve questions one, two, and three in your head, and you don't have to go through all this. I totally know that, and I applaud you for that. But what I'm telling you is that that's because you're thinking really quickly. So what I'm asking you to do is take the really fast set of thoughts that went through your brain so quickly that you thought of it as just one thought and drag them out into the many steps. It might be boring and irritating to do that right now, but the reason is that you need a model of what all the steps are that you're doing so that when you get to a problem that you can't instantaneously visualize, you know what mental movie to run. The bottom line is we need this. I know you don't feel like, many of you don't feel like you need these steps for questions that are as straightforward as this. I totally get that. And I've been there. We are building a life raft for the problems that are going to come that eventually lead almost everybody in one way or another to say, I have no idea what to do here. We're trying to avoid the I have no idea what to do here. So we're building a life raft for what to do when you don't know what to do. And the secret that took me years and years to realize is you can't build a life raft when you're already out at sea. You got to build it on land first. So we construct and practice all the steps in questions that don't seem to require them so that we've got steps at our fingertips for when they are required. Okay. So when in doubt, overdo the thinking. Everything that occurs to you as some new thought, treat it as a new thought and articulate it. Okay. So we have 2 minutes. So we do this. Okay. Yeah. And then also pro tip, you might want to write this in your notes. Note, I know we've 1 more minute. Notice I'm postponing the numbers as long as possible. I'm plugging in after I've done all the algebra or the trigonometry or the calculus. That's a pro tip for physics. It's going to get more and more abstract. So do whatever arrangements you can first. Hold the numbers for last in case you, for various reasons, one of which is if you make a computation error, you don't want it to bleed through everything. So now we can say, and we already had gotten the kx before was 30 newtons, right? Over, and the mass is 0.3 kilograms. So final answer circled, and we're done for today. Come on, come on, come on. I know we're done. And if you have to leave right now, you can. If you don't have to, I know you can go in a second, but I'm going to hang out for questions if there are any. But here is the answer. Okay, so that's the answer. We're done. You got two questions instead of one. I can't wait to see you Monday with your homeworks. I'm going to stop the recording, but you can hang out if you have any questions. But goodbye, goodbye, and thank you all for have a good weekend. Yes. Okay. Actually, I'm not going to stop the recording, but yeah, I'm not going to stop in case the recording is. I mean, in case the questions are good for anybody. But wait, actually, no, I will stop the